Okay, so linearization. Let me. I hope that I'll say it again when Amy gets back and Caitlin and those maybe listening at home.
Hi, Rose. She's not listening.
Hi, Rose. I hope you feel
Right, but
better.
when she hears it, people tell me.
Just
no.
like text us. Let us
Yeah,
know.
we
Let us
miss
know
you.
why.
It's been a while.
What? Is she sick? Okay.
Oh, Caitlin.
Caitlin, we're gonna miss you at track. Oh yeah, you weren't there yesterday.
Okay, so anyway.
Come back, Caitlin.
Come back.
I can't do it without you.
Okay, so when I was in college calculus 1 and Dr. Staten started teaching linearization or linear, when Dr. Staten started teaching linearization or linear approximation, and he called either one, I took fastidious notes as always, being the, I was gonna say excellent student that I was, but really trying to think of a word for what I was. I was one of those, like, why did I make a 99, like, crying at the teacher's desk.
So Anna.
Yeah, so, anyway, I took great notes, cause I cared a lot about my grade. Anyway, when Dr. Staten started teaching linear approximation, he's like, came in and wrote on the board, like, this is what we're doing today, and I took all these notes and wrote down this new formula. And girls, fast forward like 5 or 6 years, and I'm a teacher of calculus, and I get to the linearization section. As much as I liked Dr. Staten as a teacher, I'm like, seriously? Like, once I got through the body of calculus and I started teaching calculus, when I got to linearization, I'm like, I'm not doing anything new. Like, I didn't have to even write any of that down, okay? So I'll show you the formula for linearization. We'll probably pull it up online. And I'll show you there's a formula for it in your textbook. In fact, I'll look it up here. But I would say you don't have to write this down. It can make your life a lot easier. But first of all, let's look at the worksheet and see, listen, okay, we'll get to the worksheet. Did y'all see, did you get the feel on the worksheet that you were approximating?
Yeah.
Okay, thank you, Caroline, for saying. What in the world y'all have to do today? Oh, okay, y'all just look so.
No, I'm
intense.
just doodling.
Okay.
I have a Spanish.
I have a Spanish
and a
card.
stat quiz.
And a
I
stat.
have a stat quiz, I have a
Why
chemistry
does
quiz,
someone
and I have a Spanish English essay, and a Spanish quiz. Have a good day.
That's unfortunate.
I don't have any.
Oh, yeah.
And I also have Spanish.
Well, I have a chem quiz.
How was it?
That's fine.
That's good.
See, I can even look where it is in here.
Everyone in Calc was complaining about their quiz today.
Yeah.
And they're like, we didn't know. But like, there's math quizzes like every week. Like, you should look at your homework.
You should
They complain about it so much, and I just, everyone in Calc
they
is
really
easy.
do.
Oh. They're like, yeah, like it was
Well,
on
it's
the
also
syllabus Wednesday night. And we're like, God, it's so.
Okay.
That means you should have known about it.
All right, so, it's usually more intense than this. This is pretty good on here. So, linearization, many times it's presented like this, like L is equal to the derivative at some number C plus, see, I gotta look at the formula. F of C, I wasn't sure exactly how they wrote it in the book. F prime of C times X minus C. Okay, and so don't write that down. Okay, I was taking notes and he went all the way through. There's this chapter 3, section 9. He went through differentials and linearization and taught us how to do differentials and linearization. So he took an example like one in the book. So if you have f of x is equal to 1 plus sine x, for instance. So if I'm following the formula, my linearization, which is called linear approximation, and we're trying to find, tell what we're trying to find, they didn't really tell us, so I'll just make up one. I didn't even look at the example before I started. So let's say that I am trying to approximate f of 3, okay? I have no idea what 1 plus sine 3 is without a calculator. Granted, I could put it in a calculator, but there's a bigger point here that I want to make. We're about to approximate it without a calculator. whatever 1 plus sine 3 is. I don't actually know what it is, we're about to find out, so just threw in 3. But it's got to be close to 1 itself. Why is that? How do I know it's 1 point something small? It's not 0.9, it's a little over 1. 1 point. How do I know that? Alright.
Sine 0, 0, and like 3 is really close to 0. Like in degrees.
Oh.
Well,
So
what is
you know
calculus in?
In radians.
Those are not 3 degrees,
Well, so
but
the
same
line-
reason.
Yeah, it's
Is that
pi
what
to
you're gonna
0.
say, Emily? So same reason, it's close to pi if I'm in radians. Happen to be close to degrees if I was in degrees, but it's really close to pi and the sine of pi is 0. So I don't know the sine of 3, but it's something teeny tiny, okay? But I want 1 plus the sine of 3. So I'm gonna follow this. I'm gonna say f prime of x is equal to cosine x, hoping that I did this right. So my equation of my line is f of 3, but the problem is that I don't know anything about 3. So what I'm gonna do is I'm gonna choose, x is 3, I'm gonna choose some number c that's really, really close to that so I can do my approximation like I just noticed was natural with y'all, okay? So I'm gonna make it easy on myself and pick something that's convenient. Many times when I pick an integer, like if I'm estimating 1.07, I'll pick 1 and linearize it at that point, do my linear approximation with that. So I would only pick something like pi, probably if I'm doing trigonometry, because 3 is not any good. I'd rather use 3.14, okay? So if I do f of pi, so I'm gonna do f of c, my c is pi, plus f prime of c times x minus c. And you're still just watching. Okay, and you see how I had my formula in my notes? And I kept looking back at it to fill in the pieces, sort of like I'm doing now, okay? And so he taught us to, if you're just approximating, pick something that's close that you know. All right, so the equation of my line is f of pi, which would be 1. F prime of pi would be negative 1. And x minus pi, what's my x right now? 3, okay? Because I fill it in at this point for x. F of x is 3 minus pi. All right, so I can keep on with my estimation and do 1 plus negative 1. This would be negative 0.14159. So as far as I know pi, it's 3.14159. There's as many digits that I know. But it's good enough for now. So I'm estimating that my linear approximation is 1 plus.
I forget. I know like 40. Yeah.
All right, so is it 1.14159?
That's all I know.
Okay, wait, okay, I understand you know a lot of digits of pi, but I need to move on, okay? I confess I don't, I'm glad that you do, I think that's awesome. But do y'all see that I just got a linear approximation of that? I just got an approximation. Now, would somebody get out a calculator in radians and type in 1 plus the sine of 3? Because that's what I'm trying to approximate. I'm trying to approximate 1 plus the sine of 3. All right, what do you get, Grace?
Says it's 1.411.
Okay, 1.411?
1.4112.
Okay, I'm surprised it's that far off. Because normally when I do this, it's really, really close.
1.141.
Thank God. Okay. Yes.
Yeah.
So, literally, thank God, because my whole example just like flew out the window, and I was actually thinking, like, what the heck am I going to do now? 'Cause I just have like not at all made a good point here. Okay. So, did y'all see the shock on my face when she said 1.4? You may not have expected me to be shocked because I was within 3/10 of the right answer had it been 1.4. Okay? Look how good that approximation was.
Good job.
And if I'm told about the AP exam to round it to 3 decimal places, I did it. People do linear approximation, linearization in businesses all the time. Because sometimes curves can be very dramatic and hard to deal with, and especially if you're projecting into the future. When I had career projects in my classes, when I saw classes every day and I had time to do stuff like that, and they brought in speakers that I've mentioned to y'all before, I think. There was a group that came in from a company called WorldCom that now the CEO is in jail, but that's a whole nother story. It's like an Enron scandal they like had in their books, and it was one of those scams. But anyway, it was an up-and-coming company, and one of the biggest companies in the world. They were the first ones to lay fiber optic like wires through the ocean for like.
Oh, yeah.
So anyway, so we were really glad to have them there. I don't think the people that came to talk to us are actually in jail, but anyway, they were good engineers with the company. But they started showing my students how they were using linearization or linear approximation to make projections into the future. Because if I'm going to project $1.14 million or 1.4 yards of something, do y'all see how it's such a quick thing to do? Okay, and sometimes you don't even really have an equation, but you might know the slope of the line at that point, depending on the data that you've collected. Okay, so it's also useful if you don't even have an equation that you could even fill into. That they're doing these tangent lines to approximate into the future. It'd be amazing in a couple of months to see where else this takes us. Okay, so I want everybody to see what just happened though. What just happened is I did our topics for today, linearization or linear approximation. There's also our whole title right now, it's called differentials. And so I thought I was learning a whole new concept about linear approximation and differentials, okay? But look up here, girls. Let's take L out. I'm going to take L out and call it Y. Would y'all agree that that's okay? L stood in our formula for linear approximation. It was our approximation, so I was approximating my Y value, okay? And isn't this another Y value? This is going to be my f of 3. That's going to be my f of pi. So I'm going to say y minus f of pi equals f prime of pi times x minus pi. As a teacher of this, I'm like, are you kidding me, Dr. State? Why didn't you just have me memorize that? That's just what? This is the equation of the tangent line that you've been writing over and over and over again. Don't learn anything new. If somebody asks you to do a linear approximation, write the equation of a tangent line. What's interesting, you know how AP exams are. Most of you picked up on that on the free response that you did with the volume, by the way, that was on the first worksheet that was on the video that I gave y'all.
I know, I realized that after, and I mixed up time.
I didn't even realize that myself, but I started grading it and I thought, we've done that H minus 12 thing together.
Me and Elena did it the night before.
Yeah, blah, no.
But yeah, pays off. Alright, so anyway, the A part was write it in terms of age. That was not a calculus problem, but that was a really nice thing to do because it helped most people avoid the product rule, okay? So you just had 1/3 pi h cubed that made it a whole lot easier derivative to take. So a lot of times you'll see problems that I give you where it'll say, a lot like the worksheet, like you may not know where they're headed unless I gave you an inside track on this. They'll say, write the equation of the tangent line at 4. And you do that, because you know how to do that. You go f prime of 4, you fill 4 into the original, you write the equation of the tangent line at 4. Then they'll say, use that equation of the tangent line to estimate the value at 4.1. They're leading you right down linearization. But even if they didn't do that, I would say estimate f of 4.1. I would linearize it at 4. And I'll show you a picture of why I would do that, okay? But y'all see that, let's rework this problem in a new light. This is what I would want you to do if anybody starts talking linear approximation or linearization, okay? So if you see that you're supposed to approximate, especially linear approximate, you just write the equation of the tangent line just like old days. I'm trying to find f of 3, I can't. So I get something that's conveniently close to that because I am approximating. I want to get really, really close to it, okay? So now I'm going to write the equation of the tangent line. So I'm going to find f prime of x, and I get cosine x. So f prime of pi is -1. Isn't that the slope of my tangent line? And then I'm using the point pi, so I'll fill pi back into the original. I believe I got 1 back here. So now I'm just going to go y minus 1 equals m times x minus x. And now I want to know f of 3. So what do you always do with f of 3? You plug it in for x, okay? So I'm going to have y is equal to -1 plus -1. So I'm sorry, I'm moving this over. So that's a +1 minus 1 times 3 minus pi. You finally fill that in, which you'll do in a lot of different instances this year. And that gave us the, give me the number again, 1.14, 159. Okay, so please girls, when you're doing linear approximation, just write the equation of the tangent line, which is what I had you do on the worksheet. I didn't work the worksheet myself this year and I didn't bring my folder down, but did I ask you to, I tell you what, let's go through, do y'all want me to go through a certain one of those or just pick one? Let's do the square root one, okay? All right, so Celine, you want to read it to me, so I didn't bring my sheet down.
For y equals square root of x, and find the equation of the tangent line at x equals 16.
Okay, so let's pause, and what I would say to, they might say that in the for your spots, hang on, Grace. What I'd probably do is, I'd say estimate the square root of 17. That may be how it's given to you, estimate the square root of 17, which I don't know without a calculator. Grace? Do you have a question? Oh,
Oh,
you had
my
your hand
question?
up.
Yeah, so when I was doing it, I noticed that like different problems, the approximation difference was different. So what makes an approximation greater, like the difference greater?
Oh, I
than
erased
that?
it, or it's maybe on the other side. I'm gonna get into that differentials.
Okay.
It does sometimes, I think somebody was answering for me, like, sometimes it has to do with how far away from the X you are, but not always. So we'll talk about that. So it has to do with this other thing called differentials, okay? So if I want to estimate square root of 17, I can be really impressive here and go, well, you know, I'm not even going to get out my calculator, okay? So I'm just going to use something really close, x equals 16. Girls, that's far away. So back to what Grace and Anna are talking about is this should not be a good approximation, but it is pretty good, and we'll talk about why. Because right now, I'm pretty far away. I mean, usually, if I'm estimating 17, I want you at like 16.8, right? Okay. So I'm going to fill 16's convenient. So I'm going to fill 16 into x, and y is 4. So I'm going to say y minus y equals m times x minus x. So here's the key. You write the equation of the tangent line at something that you know at a convenient place. Okay. Now I'm going to take the derivative, y prime is equal to 1/2 x to the negative 1/2. So I get 1 over 2 square root of x. And what's my x right now? I'm sorry. Right now I do all of this with 16.
Yeah.
Are y'all okay with that?
Yeah.
All of this was your f of c, the one that you know. And at the very end, what do you fill in for x? The number you're looking for. Okay, so I'm going to fill in 17. So I get y equals 4 plus 1 over 8 times 1. So I'm going to get 4 and 1/8. What is that, 4.125?
Yeah.
All right, and then what was the square root of 17?
It's 4.135.
4.1.
Sorry. 123.
Good grief. That's super, super close. Girls, look, please. Okay? Because some of you are on physics, and some of you are on physics right now, right? AP physics?
Yes.
Okay, so this will be a little bit different, but a lot the same. If you're not in physics, then you're like me, like I was a straight mathematician, so don't worry about it. You don't have to have been in physics. You're just going through straight math, okay? You don't have to like, the applied part of it is beautiful. Most of my students actually are in physics and engineering and stuff, but if you're just in calculus, it's not gonna hurt you. Okay, so let's go back to what Grace and Anna were talking about. The difference in my x's was 1 unit. That's pretty far away, from 16 to 17. But the difference in my y's was only 0.002. I was 2 1,000th close enough without a calculator, okay? Which if you're, a lot of people like to say use this for projections. So you're even if you did it exactly, that's probably not right. Probably not right either if you're using it to project into the future, right? Okay? So the estimation's really good, but how weird is that? Is that my delta y, okay? This is my delta x if you're in physics. And I actually don't have my delta y yet. We're gonna get that in just a minute. In calculus, when we're approximating, we use a small d. In physics, and in calculus, if I know the exact difference, I use a capital D, capital Greek D, okay? That delta x and delta y to a calculus student means I know exactly how much it changed. The little dy's are derivatives to us, and they're approximations, but we know the limit is x squared to 0. You slam 2 points basically into 1, so it's an incredible approximation. Okay? Let's find our actual delta y. Somebody would, and we're going to have to round it off either way. Will somebody say 4 minus square root of 7, or square root of 17 minus 4 for me?
Minus 4.
Yeah, because you're doing square root of 17 minus square root of 16.
0.12310, like so.
Oh, that's not what I wanted then. I thought that's what I wanted. 1, 2, 3.
No, that is.
Oh, that is what I
That's
wanted.
what you
Okay, so, wait.
Because isn't
That's-
it? No, because that's the difference between like the originalized.
Yeah,
values.
this is my error in measurement.
So,
Sorry,
when
that
you
is not my delta y. I'm so sorry. My error in measurement was only 2 1,000ths. All right, so I'm sorry I said that wrong. So I'm glad I got you to type it in. The old y was 4. If I actually use 16, and the square root of 17 is actually 0.123. So if I changed 1 unit on x, my y only changed 0.123 according to the approximation. Like, this is what it was at 16. This is what we approximated at 17. Now, what was it really? It was 0.123 something more, right?
It's a lot more.
Right, because it's irrational. So what's the actual change in y? Would actually be 4 minus the square root of 17, which is 0.123 what?
1056256.
Okay, so then we can also look at that and see a really small error in measurement and how much it actually changed, okay? Now, before I tell you why that happened, does anybody know why we got so close with such a big jump in x?
Square roots are much smaller.
You're on the right track.
Close.
Yes.
Function like little stuff.
Square root of x looks like this. So if you're out here at 16 and 17, the difference is so much more negligible than if you're at something like this and you're looking at the difference of 16 and 17. Do y'all see what I mean?
Yeah.
So the rate of increase of your object really impacts, like sometimes if that thing's increasing rapidly, you don't want to move far at all, or you could be really far off. If it's growing slowly, then you can go further out and get a good approximation. Do y'all see
So
what I
if
mean?
it's like concave down, it's better.
That one, I could also draw one that's concave down, but it still kind of depends on where you are. Um,
Yeah, okay.
When is the only time that that rate of change would be the same? Over and over again. She mentioned concavity. When if I change x and change y, would that stay the same? When it's what? Linear. If my original equation was not like y equals square root of x, it was y equals 3x plus 4, then it would change at that constant rate. As m and I move a point over, we know where we're going to be because of the slope. Okay? All right, so once again, this is what you're going to do when you have linear approximation. You're just going to write the equation of the tangent line, okay? So let me do another example for you. And this is called differentials, and over again, if you look in the book, they're using differentials. Okay, so I kind of want to do a different problem, but I guess I'll do this one. Because I really stumbled through that little delta y and dy, so I want to make sure I make that clear. So we're going back to y equals x squared for a minute. So I want to completely follow this example in the book. So if I'm at f of x equals x squared, and it says find dy when x is 1. All right, so we're looking for dy when x is 1. That's what we're looking for. And dx is 0.001. All right, and then later on we'll compare delta y and little dy. So stay with me with this capital stuff and you know, don't tune me out if you think, oh, I got the equation of the tangent line. All right, so I really must be trying to approximate f of 1.001. Do y'all see what I mean? But there, I'm using 1 instead. other ways. High time I showed you why this works. Because if I have a curve and I fill in usually an integer, and this is a trig function, then I'm probably going to fill in something like pi over 6 or pi or something. But if I fill in a number like 3 and I write the equation of the tangent line, it's locally linear. Girls, please look. Don't look at your computers. You're too old and I trust you too much to say close them, but please watch. Here's f of 3. They share that point, okay? I know 3 on the equation of the tangent line, and I just locked it onto the curve. But for a period of time, they stay incredibly close to each other. If I zoom in on that area, sometimes it's really hard to see the difference between the two. So you're actually going to take like maybe 3.02, and you're not really filling it into the curve. You're filling 3.02 into the line that you created. But do you see why it's such a great approximation? Now, do I want to go too far? It depends on the shape of the curve, right?
Yeah.
Okay, a lot of times though, your safety net is usually not your choice. They'll usually say, here's this and here's this. Here's 4.04. You would write the equation of the line at 4, lock it on, and then fill 4.04 not into the curve, but into the line. Do y'all see what's called linearization or linear approximation?
Yes.
Super safe. It's like you can walk out of here and go, I don't learn anything new today in calculus, okay? Please don't do that. But that's all you're doing is writing the equation of the tangent line. But I want you to always think of why. It's going to be really interesting as the year wears on, because there is something coming that Euler found that we could do if we're way out there, which right now we have no business being way out there. We could be many points off, they'll start to separate. Okay? All right. Back to what Grace and Anna brought up though. It's interesting, if you're far enough out on the square root graph or one that's growing really slowly, like a logarithmic curve or something, you're pretty safe. You can probably estimate something a lot further away. All right, let me move on. So what I'm going to do is take the derivative. Oh, I want this to be, oh yeah, they did use x squared, so we haven't done an x squared yet. So this is 2x. I'm writing the linearization at 1. So I'm going to say y minus y equals m times x minus x. Okay? I need my point, so I fill 1 into this, so I have a 0.11. And the slope at 1 is 2. So now what just happened is I have this curve, and I just locked on at 1 and wrote the equation of the tangent line. Now I'm going to fill 1.001 into the line and not the curve. It's going pretty steep, so it might be further off than we expect. But it's not super steep at 1 yet. It gets steeper as I go, okay? All right, so now I'm going to fill 1.01 into that, and I get y equals 1 plus 2 times 0.001. So I get y is equal to 1.002. All right, so that's my estimation. Would somebody please fill in 1.001 and square it? So f of 1.001 is actually what?
1.002001.
Good grief. What a great approximation, right? That's fantastic, okay? So you can see how easy it is to work with a line. What function do we all like best would be a line, if you got to do it, okay? So my point, this is what I didn't say very well before, that I need to say better now. My point was 1, and the answer to that, to 1 squared is 1. If I move away from it by 0.001, my approximation was 1.002. These are my x's. It said move away from it now. You're changing x. You're going to move a positive 0.001. They might say negative, and you move back to 0.999, okay? You can go either way to use your approximation. And so you got to look at your delta. And then if I fill 1 into the original, I don't want to do that. I want to do, that's where I messed it up last time. Oh wait, I do want to do that. Okay, so my delta x, my dx is 0.001. My dy is 0.002. Now this is what I was preaching, please watch, okay? In math, these are, in calculus, These two are interchangeable to us. Okay? You'll see me, I'll interchange little d and big D all the time, because if you tell me to move 0.02, that's my exact change in x. So it's really immaterial which one I call it, okay? It's my change in x. It's my exact change in x, or you could call it my approximate change in x in a differential, which I really haven't still defined for you. But my approximated change in y is 0.002. Do y'all see I'm saying if I move 0.001, in this instance, it moved by 0.002? But what was the actual change in y? Was 0.002001. Do y'all see there's a slight difference? But the whole point is that you see why I like calculus, because it does a good job of estimating things that we need to do. Many times you're not doing something that's exact anyway. I'm not going to do it. There's years that when I see my students more often, we actually do some machinery problems. Like, the measured radius of a ball bearing. So if you're at a company that's making ball bearings for something, like all sorts of stuff that have to roll. Y'all seen those little metal ball bearings that? So, you know, there's quality control at plants because they're not all going to be perfect. Okay. Have you ever wondered, like I do, where the quality control people are at the Doritos processing plant? Does anybody know what I mean? When you get a bag of Doritos and you feel like there's 4 in there, and I'm like, how did this pass quality control? It was supposed to have a
And
lot.
also, like, some of the little, like, things of Welch's gummies, like, they have different amounts in each one.
I feel like
I'll start to pick things up and try to feel like how much they
Like, why
have.
would they let that go?
I
It's
know.
so neat.
I'm like,
and
why would
it's
they
like, you would think
But-
that machinery would have advanced.
They have like
So neat.
ethical standards in place where people check up on them and all of that.
One time I was
So
like,
girls, listen, if they say that my bag of Doritos is gonna be however many ounces, do y'all realize that by the weight of each Dorito, it'd be hard to have that exact amount of ounces every single time? But it should be within a certain area of measurement before they let it go on into the bin, okay? So these ball bearings are supposed to be 0.7 inches and they're coming out of the machine. From what I hear from people in this kind of work, the machines can get off kilter and they have to be recalibrated. And so they want to watch for that, because if the ball bearings start to not be 0.7, they won't fit in what you need them for. And so they know the measurement is correct within 1/100th of an inch, estimated the propagated error in the volume of the ball bearing. So what happens is somebody could be standing at the end of the line and go, I'm throwing these away if they're not within 1/100th of an inch of how big they need to be, and I'm going to go find out who's doing that maybe and fire them, okay? Like, why have you not recalibrated the machine? Because now these ball bearings are not within 0.01, and they're not going to fit in whatever machine we're selling them to, or getting bad reviews online, because, girls, we've all gotten something that doesn't fit, okay? Like, for instance, isn't it aggravating when the top of your pen is loose and it doesn't snap on?
Yeah.
But there's a certain area measurement there that is allowable. Isn't it aggravating when you order something, you start to put it together from
That's what I was
IKEA?
gonna say, IKEA furniture, I just said that.
And one piece doesn't fit into the other one.
Put together a bookshelf and there's like one spot that just doesn't go
And you
together.
can't make it fit. And it's because they got outside the error measurement. And so here's the deal. I could be standing in the line, but I don't have to be as smart as the people figuring out how to make that happen. So I want this little sphere to have a volume area measurement of 0.01. But you've got to figure out what kind of error you can have in the radius to make that happen. Do y'all see what I mean? You go back to 4/3 pi r cubed, take the derivative, linearize it, and you can tell somebody, while you're making this, the radius better not be this far off, or when it comes out at the end, it's going to be wrong. You don't want to just find out it's wrong. You want to know what error measurement you have to create an error measurement here, okay?
Yes.
And depending on what people allow. I'm going to move on. I keep saying this word differential, and so let me make this clear since I stumbled through it the first time. These two to me are interchangeable. This means this is my linear approximation of how much the error would be. Notice, girls, that's not my y value, that's the difference in my y values. How will you always find this one then? You'll fill in the point you tried, you fill in the point you're looking for into the original, and subtract the two. Which you have a valid question like, then why am I linearizing if I'm going to fill the point into the original? you're only gonna linearize if you're really never gonna do that. I think the exercise in math is to show you how good you're doing, okay? Stay with me, because many times people are just working with data. They don't even have an equation for their data, but they can figure out the rate of change out a certain, based on their data. They may never even write an equation for it, and they can still linearize it as long as they know the pieces, the components. A certain point and the change of rate at that point, okay? All right, so, here's what a differential is. I took notes on this too. You don't have to. So Dr. Staten's like, and probably most math teachers are like, okay, so today we're going to use differentials. And he wrote on the board, dy equals f prime of x dx. I don't think I'm going to give you homework out of the book. You almost should hate me for it because you have like equations like this in the book. X squared plus 3x plus 7. And the instructions say, find the differential. And all you have to do is say dy equals 2x plus 3 dx. Now while I'm saying you don't have to write this down and you are not learning something new, I do need to explain what just happened. And it goes back to what I've been teaching all day today after ducks and sinkers, okay? This is saying I estimate my change in y by using my slope of my equation times the change in x, okay? So let's do one and then we'll revisit it. So let's say I want to find f of 2.01. I don't really feel like filling in 2.01 squared plus 3 times 2.01 plus 7. I mean, I could, but I don't really want to. So what I'm going to do is I'm going to say I think my change in y is equal to the derivative, but I'm not going to fill in 2.01 into this. What am I going to fill in? I'm not going to use 2.01. I'm going to use 2 temporarily to estimate it. So if I fill 2 into the original, do I get 14? No. 17?
13.
I'm getting 17.
17.
17. Okay. All right, so my slope is 2 times, I'm using 2. So I have 7. And what was dx? They wanted me to estimate 2.01, and how far is my delta x? How far off am I? If I'm using 2, 0.01. So I'm saying this is 0.07. What is 0.07? I'm not saying the answer is 0.07. What am I trying to predict? What does dy mean?
17.
Okay, so what does dy mean all by itself? That's saying how much my y changed. Girls, dy over dx, this is a y minus y over x minus x. We're running around calling it the difference quotient. I didn't put all this together, so, you know, I hope y'all are. When I say dy, I'm saying I think that's the difference in my y is approximately 0.07. Now let's actually find it. So now we're going to find delta y. So I'm not even saying what y is yet, okay? Now somebody said it, Emma, is predicted it's going to be 17.07. Do you see how she's got a dx? And if dy is 0.07, this should be 17.07. All right, a couple of people please go and fill in 2.01 squared plus 3 times 2.01 plus 7.
Plus 3 times 2.01 plus 7. 17.0701.
Okay, so it's actually 17.0701. So our little dy, our differential is 0.07. The actual change in y was 0.0701. So a change in x at this moment on the graph of this parabola, a change of 0.01 resulted in a change of 0.07. So you kind of learn, like, at that part of the graph, you're about 7 times at risk on your y value than you are your x value. It's growing kind of fast there. Isn't that phenomenal though? But the big deal is I want you to see the difference in little dy and capital dy in a math class. In physics, I think you tend to use a lot of delta x and delta y for derivatives, which we wouldn't. We would use little dy over little dx, because every time I write the equation of a tangent line, I'm approximating. So do y'all see the difference for us? Little dy is, this is what I'm estimating. Capital D is you actually found both of them and found the difference. Okay, again, why is this nothing new? This is a differential. dy. Did y'all see what I did to approximate just the change in y? Did y'all see that? I want y'all to see two things here. What is dy over dx anyway? So all he did was just slap it over there. Do y'all see what I mean? They've separated. They're like, oh wait, I want to focus on just my change in y based on my change in x. Look at this, girls. dy, isn't that the difference in my y's? Isn't this my slope? And isn't this the difference in my x's?
Yes.
It's all the equation of the tangent line. Okay? All the way back to algebra 1, where you learned this. y2 minus y1 equals over x2 minus x1 equals m, right? Girls, if I rearrange that, I get y2 minus y1 equals m times x2 minus x1. A lot of y'all know that is what you're doing. All you're doing is writing down the slope formula. Rearranged. So how could I rewrite that last statement I just circled? What's y minus y? My change in y equals m times my change in x. So I have dy over dx equals m, which in calculus is your derivative.
So basically we
Equation of the tangent line. Equation of the tangent line. Okay? So let me say this, then I'll get Grace's question. So I do need to end this topic with this. If they say y equals 7x cubed and they only ask for dy, don't just say 21x squared. Okay? Y is not just going to up and change all by itself. That's literally impossible unless you have a constant. Okay? And it doesn't change. Y is not going to up and change. Doesn't it have to? That's got to be somewhere. So that's what differentials are about. That other change has got to be somewhere. Okay? Please don't forget your question because I got to finish this thought. Okay? So if I have area of a circle. All right, if I have area of a circle, then what does this mean? A prime. F prime, doesn't that mean dy over dx? In this context, you're going to have to learn from here on out to follow your variable. I say that a lot, okay? Follow your variables. I don't have x's and y's in this, I have a's and r's. So what would a prime mean? That's a dA over what? dr. The area is not going to change unless I change the radius, right? Unless it's a related rate problem, then it's a dA dt, dr dt. But do y'all see what I mean here? If I have y is equal to 7x cubed, y prime is 21x squared, but y prime is really dy over dx equals 21x squared, okay? So A prime embodies the difference quotient, the change in area over the change in radius. How did my area change based on the difference in my radius, okay? A2 minus A1 over R2 minus R1. So what in the world would you do with this? I'm just asking for the change in area. That's a differential. So you would say 2 pi r dr. That's got to be somewhere. So they are really isolating, like I did today, the change in y, not the slope. If I move this over here, it makes perfect sense to me why that works. dA to dr is A prime. So if I just say find dy, what do you need to stick at the end of your equation is a dx. That's doing differentials. So differentials are this. Okay, if I have s is equal to 5t squared, what is s prime? That's DS over DT. So if they just asked me for what's the change in S, I would say 10T, but what has to be somewhere? DT. If you want it as a derivative here, if they just say find DS, don't forget to multiply the other side times DT. That's how I was getting all these problems right. Everything I've done today is not new. You could walk out of here and go, let me do the equation of tangent line for 45 minutes. Okay? But it's a gift to you because my teacher came in and I took all these notes on differentials and linearization and new formulas. The great Dr. Shane, he may still be at Ole Miss, he's still there.
Oh my god.
Which is next to impossible to forget, but I can see it in the last 10 years. Anyway,
No, just typing song.
Google it, Dr. Stater.
Doctor who?
Dr. Staten, John Staten, University of Mississippi.
Yeah.
Let's see.
Well, Carolyn's seeing that. Is his first name Bill?
It's John, I think. It's been a long time. I don't remember. His last name was spelled funny though. He was.
There's a Bill Staton, like O-N, who is also a math teacher. That's kind of freaky. Yeah. Oh, yes, they're Ole Miss. That's. Maybe his name was John. Bill John.
Maybe his middle name.
It's not Stan. Oh no! I remember that it was.
Is there like a roster of math teachers? Yeah. How do you know?
Well, if we know that if he's not.
There could be a
Oh, is this him?
You know that one
Ah, past the S's, no state, and he's not there anymore.
Yeah,
Okay.
this was on that website.
So, all right. So anyway, probably should minimize that one.
You know.
Okay. So are y'all okay on the worksheet that I gave you?
Yes.
That just led you to discover linearization. So your homework is going to be what you'll see posted is a link. I didn't and not going to print out a 2003 40-page packet for you. My guess is that most of them are printing off in the Math Center anyway, so it's sort of a moot point. But that you'll have access to it online. Some of them I won't do that because they're copyrighted and you should buy them from the College Board. But with them being released to the public, I'm sure you trust me, I'm super good at it. So I'm not going to hand you something that's not legal for us to use education on. So you can print it, but some of you may not want to print it. You just may want to pull it up on your computer every day, do it for homework, do it in class, whatever. It's up to you. I like to have a hard copy, but I know people are different ways. Or you can run off the parts you need, copy, and then do some more later. We'll eventually finish all of the 2003 exams. Your homework will be on the 2003 exam. Okay?
Yeah.
Oh, and check with me constantly about your test grade. Sorry about that.